I haven't met a lot of you guys in here. So my name is Ryan Polis. I'm on the same team as Matt. So I also used to be a former system engineer. I am also now an application engineer again. So I was in the past, and now I am again. So the whole point of this presentation today is to kind of show what I call like C-style programming tips in LabVIEW. So it's ways to do more explicit memory management, stuff like that, as well as calling different kinds of C functions and functionality from the standard C library in LabVIEW directly. One of the reasons I made this presentation is because over the years in SE I've done a lot of work with our customers to integrate LabVIEW with a lot of other languages. So we've had a lot of customers who are doing, they have like a LabVIEW application running on their real-time target in parallel to like a C process running. And they're like, how do we share data between them? How do we synchronize the threads? How do we do all sorts of stuff like that? So I kind of got started doing a lot of work there. And in the process I kind of wrote a lot of libraries and kind of came up with some stuff that was pretty useful. And a lot of people were kind of like, you should kind of wrap this up into a presentation. So this is the first kind of run of that presentation. So feel free, if there's some things that you think are worded weird or something, let me know. And I'll take that feedback and make improvements. So with that said, what I'm going to kind of go through, and I'm going to try to keep it pretty quick, I'm going to go through and talk about the LabVIEW Memory Manager. So I'm sure everyone in here is probably pretty familiar with that. But I'm going to go through and talk through, how you can utilize it manually in your LabVIEW applications to kind of do manual memory allocations. Then I'm also going to kind of jump in and talk about the standard C library and kind of how it's loaded and linked to LabVIEW and how we can actually utilize functions from the C library directly in our LabVIEW applications and BIs. And then I'll kind of go through and talk about some of the examples and use cases you might be able to do with some of this stuff. So with that said, the LabVIEW Memory Manager, none of you guys have ever used it. There's public-facing documentation online. You can go and look at the LabVIEW help and view some of this articles that kind of talk through all the different functions that are available. But the idea here is that the LabVIEW Memory Manager is kind of like the core underpinning in LabVIEW that does a lot of the key allocations for all the data types and all the different handles and pointers that are needed for the VI to execute. The thing is, all of these are kind of publicly exposed, so you can go in and actually call these with a call library function node yourself and kind of do allocations and stuff manually. So for example, you can do things like allocate and release handles, you can resize them, you can do all sorts of stuff like that. Obviously with pointers, you can allocate and dispose of pointers and get some stats for the memory as well. So obviously the key memory manager functions are going to kind of map directly to the kind of same memory allocations you might see in a C application. So just like you have the malloc function in C, you're going to have your kind of dsnew pointer in the LabVIEW Memory Manager. Same thing with like disposing of pointers. You have your free function in C. You also have your key way of actually shuttling data around is the move block function. So you can actually give it a source and destination pointer, and then say how many bytes you want to move between the two. And then same thing for swap, which is very similar, except it actually just swaps in number of bytes between the two pointers. So what I'm going to show today is a library I wrote to kind of encapsulate all of this and make it more easily usable in LabVIEW. So it's LabVIEW Memory Manager Palette. And basically what it does is it wraps all of these key functions I just showed you a second ago, with the exception that it doesn't do handles yet. It's focused purely on pointers for now because I'm using it a lot in Veristand with real-time applications, so we kind of want static, non-relocatable blocks of memory. But the idea here is that the Memory Manager palette is going to kind of go through and try and do all the heavy lifting of some of the more complicated things for you so that you don't make mistakes. It also does all the bounds checking and null pointer checking and stuff like that so that you don't crash LabVIEW when you kind of dereference a null pointer or try to. It's going to hopefully catch all that stuff for you. So kind of looking at some of the functions here, they're pretty straightforward. So you're going to have your typical way of creating and allocating a new block of memory. So you have your new function. You take in some size of bytes, and it's going to allocate that pointer using the dsnew pointer function for you. You've got the dispose, which is going to obviously take that pointer and then you can deallocate it. You've got a subset function, which lets you take in a base pointer and then create new pointer objects that are subsets within that. That does bounds checking to make sure that the subset pointer you're producing is within the bounds of the allocated pointer you already have. And then I also included an encapsulate function. So if you have like a third-party DLL that returns like a U64 pointer, and you want to encapsulate that into one of these pointer objects, you can manipulate it with this library. You can do that as well. So along with being able to obviously allocate and create the pointers, we always have to be able to access the data within the pointer, right? So we're going to have our key read and write methods. So these are polymorphic methods, right, that you can do all the standard data types, as well as strings and booleans and stuff like that. the thing to kind of keep a note here is that these are just functions I provide, but the thing is you can also implement your own mechanisms for reading and dereferencing the data yourself. So if you want to, I'm doing numeric types and stuff here, but you can also do read and write clusters to your pointer. You can do much more complicated structures than that if you kind of know what you're doing. So that's just kind of one thing I want to show. So each of these, when they function, this is kind of how it looks on the inside. There's a lot more code than I'm showing here. I'm kind of keeping it simple just to keep the point clear, but there's a lot more error handling and a lot more kind of qualification of the pointer up front to make sure it's safe. The idea here is that when you do a read or a write, what you're really doing is you're just calling to a move block. You're going to have some kind of address. You're going to offset it if you need to, and then you're going to pass in like a wire of some kind. In LabVIEW, you're either going to pull data from that wire or move data to that wire fundamentally. So if you want to do an array, it's the same process. We'll typically have like some kind of count input, and then we'll kind of shift that to create the actual amount of bytes that we want to move, and then move the data either to or from the array wire. So it also has some other kind of nice functions to make available for memory management. So it's got copy all, duplicate, and swap. So obviously, as copy suggests, you can just copy n number of bytes from one pointer to the other. Copy all will automatically say, okay, I know how many bytes are in each of these pointers. I'm going to copy all of the data that's in source to destination, assuming destination has enough size. Duplicate, as the name suggests, it lets you take in a pointer and basically allocate a new pointer that's exactly the same size, and then copy all of the data from the source pointer into the destination. You can also specify a different type. So this is object-oriented. It's a class-based pointer, so you can actually inherit from the pointer class, create more specific categories of pointer if you would like to. And I'll show some reasons why you might want to do that here in a bit. And then, of course, there's swap, which is uses the swap block method, so you can swap some number of bytes between pointer A and pointer B. There's also the clear function. So clear is a way you can clear any kind of, you can clear all the bytes in a pointer that you have allocated. You can also clear like a subset. So if you want to do like a clear of a subset, so you can do kind of an in-place replace of some of the data. You can do that as well. Very similar to the move block function, we're going to call in a clear mem. It's going to do all of the kind of getting of the address, setting of the size, and kind of a lot of the math part for you to do the clearing of that memory. So one of the things I added for the pointer class is, in the world of LabVIEW, we have DVRs, right, which are kind of like pointers. They're reference-based for sharing data, but they have a mutex associated with them that lets you kind of lock the structure so that you can keep, in multi-threading scenarios, you don't have data corruption, multiple things trying to read or write the data location at the same time. So in this pointer class, you also have 4 overridable methods that you can actually implement with a child class. There is a base implementation, which I'll show here in a second. But the idea is you can override these 4 methods to add some kind of mutex-based locking mechanism to your accesses. So if you want to specify some kind of, well, actually, I'll just show the base class does it with a single element RT FIFO. So it basically just creates a single element RT FIFO and then uses that to kind of arbitrate the access to the pointer if you want to. So the typical read and write methods don't use this kind of locking mechanism, but I have separate methods that will utilize the lock, which is these right here. So protected read and protected write. So what these will do is they'll actually utilize the lock and the unlock to make sure that it gains exclusive access as best as it can, obviously, to the pointer, and then it will actually do the memory operation that you asked for. One thing I want to also point out, one of the good use cases for having the overridable lock methods is, in the world of Linux RT, with a lot of our targets running now, like I said, with my experience in SE, we have a lot of customers who love to do things with languages, alongside LabVIEW. And we get questions all the time about how to pass data between the two. And one of the things a lot of people bring up is that it'd be nice to have DVRs in external code that's easier to access because it kind of has that shared mutex that kind of keeps the data safe. So the idea here is that what you can actually do for that if you override the pointer class to implement your own locks, you can actually use locks that, like an interprocess mutex from the POSIX library, to actually set up like an interprocess lock that will lock across not just the LabVIEW process, but across C, Python, whatever parallel running applications you may have. So I'm going to go ahead and talk about a little bit more, actually going inside of some of these VIs to show kind of the design and the structure. So looking here, we have kind of our standard read VI for reading an array of doubles. So inside of that, this is kind of what the actual core looks like. So what we first do is we first do our parameter checking. So this is kind of the upfront check to make sure that, hey, the operation you're about to try and do, is it in the bounds of the pointer you have allocated? Is it not going to cause, an access violation and cause a crash? And then if that all passes through and there aren't any errors thrown based on the parameter checks we do, then we do our no check read is what I call it. So the reason I have this VI with a red border is this is the one that will crash LabVIEW if you have the parameters wrong. So if you have the pointer not allocated correctly, or you have the buffer's not allocated correctly, or you have the offset set too high, and you run this VI, you won't see anything, it'll just disappear. LabVIEW just won't be there anymore. So it'll be like a seg fault, so it'll just go. So the whole point of this library is that it does the checking and qualification for you, and it will throw runtime errors if you have something set wrong. So instead of getting an access violation that kills your application, you'll actually get like an access violation error instead that you can maybe in theory possibly catch and do something about.
Yeah, question.
Yeah.
Pretty thorough and elegant. But why would you use this?
Yeah, no, that's a great question.
It's cool, but I can't think of a use case.
It's really useful for. I'll show you some with like shared memory in a second with C.
So give you an example is like you're running an application that you're trying to share dual port RAM. This would be ideal with something that already running that is acquiring data and you want to plot it with LabVIEW.
We have a lot of customers who do shared memory applications to do processing with C libraries instead of using LabVIEW. So in the RF world, I have like Seb and some other guys in the RF SE team used the shared memory library I made a couple of years ago to do basically processing for RF applications. They'll basically beam all of the IP data from the RF application through shared memory and then process it somewhere else. So in those scenarios, with the old shared memory library that I had, I was exposing the pointer as a raw U64. So it was very likely that if you weren't careful with how you did things, it could crash something, which is where this library kind of came from. So I first had a lot of memory manager stuff that was just the U64 kind of Wild West style. You could do what you wanted, and if you weren't careful, you would crash LabVIEW, right? So I decided to go a little bit one step further and kind of add a little bit more of the niceties on top to kind of check the bounds for you, which is kind of where this library came from. So yeah, if you're doing just pure LabVIEW, LabVIEW's already got plenty of data communication mechanisms, stuff like that don't necessarily warrant the need for something like this. I will say what is nice about this, though, and I have it kind of pointed out at some of the points at the end, is that in LabVIEW everything is very strictly typed. The trade-off here is that this is not strictly typed. You can allocate a pointer, and it's basically a void pointer. It's just a memory space that has no type associated with it. And so if you want, you can write a double to that and then read it as a U64. It's not going to stop you from doing that. You can't really do it in LabVIEW if you have a double wire. If you want to turn that into U64 wire, it has to do some kind of copy or some kind of translation or moving it over to a different location in memory to have that extra wire having the different data, which can be problematic at times if you're trying to do a lot of in-place stuff. The other issue is that we ran into that a lot with Veristand, because Veristand forces you to use doubles because every channel is a double. But if you want to we're trying to make some stuff not long ago that did a lot more bit packing and stuff like that was more kind of integer-based operations. And what we found is that a lot of the custom devices that were doing some of that were using a typecast function, which in LabVIEW is like a double buffer copy, and it really was just like killing performance to try and take your array of doubles, turn them into arrays of U64 so you could do some kind of integer processing to them. And so this kind of helped alleviate that, because what we can do is we can actually encapsulate the Veristand channels, the inline engine channels, into a pointer, so we don't actually do anything with it. We just encapsulate them so that when we dereference that pointer, we get the data from the Veristand engine. And I'll actually I'll kind of pause there because I'll actually have slides on that later. But no, that's a good question, because it's not always clear exactly how you might use this in LabVIEW. But when you start trying to do things with other languages, that's where it becomes very nice, because if you receive like a DLL call that returns like a pointer to you, you can just encapsulate with this, and now you can easily manipulate it without having to worry about the move blocks and stuff yourself, right? So I'll go ahead and jump into, so I just showed like the parameter checking and then the core kind of actual function that does the moving of the data. So I'm going to go a little bit deeper into the check subset here, which is like an example of one of the parameter checks you might do. So inside of that, what it does is it just does some basic math to kind of check against the private data of the class to make sure that hey, the offset and the length and whatever parameters you're providing aren't going to cause crash to LabVIEW. If those conditions aren't met, what it does is it then will throw an error. The errors are all designed to be just kind of private members of the class. I think they're actually protected so that child classes can throw the errors if they want to. But I want to actually go through and talk a little bit more about these errors, because the whole point of this presentation is C-style programming, and one of the things that I did in the design of these of errors is I wanted to make them as static as possible, so I wanted to avoid dynamic kind of runtime memory allocations when building the errors. I've talked to Benji in the back a lot about this, in a real-time environment, a lot of the error handling in LabVIEW, if you use like the general error handler, they do a lot of like dynamic string building and stuff like that. One of the things we've talked about is, in a real-time environment, do you care about determinism when you enter an error state? Should you care about the fact that a lot of your errors might be, jittery or causing a lot of allocations at runtime? So what I did for this particular setup is I create a library. It's within the memory manager, actually, so it's just a little separate lib within inside of it. But it's called static error handling. What it does is it actually allocates a fixed size block of memory on the block diagram. So what it does is it starts with like a static string, and then it builds that into an error cluster of a known size. So you can say, like, I want a error cluster that is exactly 512 bytes in memory. It will pre-compute that, and then go ahead, not pre-compute it, it'll statically pull the string into the error cluster, and then from there what you can do, and if you obviously flatten out the string, you get the exact size you want. But what then you can do is now you have the static string, so instead of dynamically building your error cluster, what you can do is you can string along these VIs that use the integer offset of the current location in the buffer to actually kind of build up your error with almost like function calls, basically. So you basically chain along that kind of pre-allocated error cluster, and then you go through and you manipulate the contents of it by inserting strings and certain offsets and stuff like that. So for example, if we wanted to do like the set VI source, right, so this is what the inside of that looks like. It's going to take in a VI name and a library name, and it's going to go ahead and statically put that into the already allocated cluster. So all of these VIs don't do any kind of memory allocation. There's no kind of jitter that would cause determinism, your determinism of your application to break. Write string is the one that everything else uses. It's an in-place replace of an array of bytes, right? So it's already a pre-allocated array that we're just going to insert our data into. And of course, if you want to write an integer to it, it's going to convert that to a string and then obviously call the write string function to insert that. The cool thing about that, though, is say if we have a situation where we allocate a pointer 80 bytes and we want to write 15 doubles to that. So quick math, 15 doubles is 120 bytes, so that's more than we have. So what's going to happen is when you run this, it's going to throw an error, and this is what the error is going to look like. But the cool thing about it is the error actually is, because it's a function to actually throw the error, and it has arguments of its own, actually taking those arguments to actually put them into the error cluster as extra information. So it'll tell you, hey, your pointer was 80 bytes. You tried to access it by providing me an offset of 0 and a size of 120. That's not allowed. So you got an access violation. It also applies if you have, the offset is too high, but the data is still small enough to fit within it. You're still going to get the same error. It's just going to say, hey, the offset this time was 50 and the size is 40. That still exceeds the max 80 that you want. It also applies for like null pointers. So if you have code upstream that allocates all your pointer objects and something goes wrong and they don't get allocated and they're just kind of default LabVIEW class objects that are the pointer type, that is a null pointer because there's obviously not a valid address and size inside of that. And that's what this library also catches. It'll catch that it's not valid, it hasn't been allocated, and it'll throw the null pointer error for you. So real quick, I'm going to exit out of this and show just real quick run example of this. So I have a mini VI that I wrote just for testing. It's called Memory Benchmark. I was going to run this on a RT target because it runs much cleaner on that, but because my laptop is on battery mode. But I'll go ahead and run it on this just to show you what it looks like. But basically what this does is it allocates, well, in this case you have a start size and an end size, and it does a sweep. So it'll go through and kind of sweep through and do memory copies all the way through. It's very jittery on my laptop because I'm in like 1.2 gigahertz battery mode, so it's extremely slow right now. But if you run this on like a real-time target, you get like a nice clean line that actually tells you the memory profile of what the performance is at different transfer sizes. And I'm going to rerun it really quick so that it overlays the lines that I wanted to overlay. But what it'll actually do is it'll overlay like L1, L2, and L3 cache sizes on top of this. You can kind of see where the cache acceleration is happening in the memory. So we can see kind of our peak bandwidth in this case was like 28-ish gigs per second, which a lot of that's coming from the cache acceleration because the DRAM in this laptop is not that fast. And you can kind of see it a little bit really noisy on this laptop. You can kind of see it stair-stepping down as we approach the different cache size thresholds. Go ahead.
Finish this out.
Well, that's basically it. Yeah, so this is just a quick way. This ships with the VI package for the memory manager, so it's one that comes with it, so you can just run it But basically all it does is allocates the pointer, duplicates it, so we have 2, and then it just does varying, copying varying sizes all the way up to the max, and then displays the results. And
what's the advantage of this over the external DVR?
well, so the external DVR, I've tried to use those in the past. As far as I understand, this is my lack of understanding of external DVRs. Last time I looked at them, they seemed like you could only allocate them or create them within a DLL call external to LabVIEW.
They're meant for the external section allocates memory and then provides it in a buffer that is then lockable and controllable inside of you.
What if you wanted to go, so here's the thing, what if you wanted to go the other way? What if you wanted to provide that same mechanism to a DLL?
As in, you want LabVIEW to allocate it?
Well, or just have like that same kind of lockable DVR structure, but like I don't necessarily want it can't always be created in the DLL and provided to LabVIEW. Like that's often the case, but there's going to be many cases where that's not necessarily possible for us. So, or we don't have access to the code that we can't modify it to add that call that creates the external DVR. That's usually the bigger issue, is that it's customer code, where we can't easily add that.
You can always create a DLL that does that allocation. You just create a channel on DLL that does that, write a quick piece of C if that's what you're needing to do, or whatever the language is that your DLL speaks, all that allocates and passes. But that gives you the memory buffer and the locking structure all together. You mentioned making the lock overridable. That was the thing that caught my ear, like maybe there's some goal there.
It's so you can add your own implementation. So I chose for the default base class in LabVIEW to use an RT FIFO single element. But as an example I gave is if you wanted to have like an interprocess, like a pointer that could be locked on an interprocess level. So locked from a LabVIEW process, C process, Python. You could use a POSIX API interprocess Mutex. And you could actually override the class and implement the create, the destroy of the interprocess mutex and use that as your lock.
You're not overriding an abstract base class, you're overriding the concrete class?
I don't know if I have the terminology correct. Yeah, that's the thing is it's not fully defined where we have like a base class and then like an implementation, so the base class has implemented code inside of it, but it's just RT Python.
It's not carrying any data around it. The private data cluster, so the base class?
No, it has like the size and the address parameters and some of the core things that all pointers will have, I guess. But so it's only got like I think 4 fields. It's got address size. It's got an internal Boolean for me to be able to track whether it was given to me from a DLL or not. And then I think the RT FIFO reference for the lock, and then you can add to that if you want to. But
really needed abstract. Yeah. Well, so what you're demoing has some uses and is interesting. It is very similar to a pattern that customers very frequently try to replicate. Reference to a class, child class has another reference to a class, child class has another class, and you don't get locking through the entire system when you call a base parent class method, and it leads to a lot of nasty race conditions when you start doing that inheritance.
Yeah.
What you were trying to structure, because there's safe ways to do it, and
yeah, and for the locking. So the locking is one of the things I added very recently, just for the reason the rights. But I actually was debating whether it would make more sense to do it in like a child class that's like a lockable pointer or something just completely separate from the base class. And I was still on the fence of whether I should do that or not. So that's why this isn't like released to the public, because it's still kind of in the things are changing phase. So that may be, that's the kind of feedback I'm actually looking for, is like, if there's situations like that you're aware of that make more sense to do it a different way, I'm all for that. Because
if your lock function is not dynamic dispatch, it's just static dispatch, it'll give you a dodge an entire class of bugs.
Yeah, it's dynamic dispatch right now, but
yeah.
But yeah. Oh, sure. Yeah, go ahead, Chris.
Can you get access to RT FIFOs without having your RT installed?
Well, that's why I made it overrideable, because if you want to do not in LabVIEW, you probably can't use the RT FIFO.
Well, if it's in your base class.
Well, yeah, so that's why I'm going to probably make it a separate class.
Yeah, that was my question.
Yeah, right now, if you inherit and you make your own customization, you're still going to have that FIFO ref that's still there, but like, I don't want that either, but for the sake of getting this running for someone else recently, I had to do it that way. But I would like to make it as a separate class.
I thought RT FIFO was going to work on my computer.
I thought that was a great they would work on that. I don't know if you can get them down small and LabVIEW RT.
Right, and they don't work on Mac.
I don't know, yeah. Don't know about that, yeah. Cool, so I'm going going to try to make this real quick because we're kind of running out of time. So I'm going to switch gears from the memory manager side and switch to the standard C library. So this is a little bit more interesting for some people. So I wanted to get the memory stuff out of the way because it's kind of important for this part as well. So real quick, obviously you guys are all aware of the standard C library. I'm not going to go into details of what it is. Obviously it's the library that is like the core of C, and it's always implicitly linked to pretty much every C application. You just don't even realize it. In Linux, you know, on our Linux RT targets, it's obviously in the standard libs folder. It's the libc.so.6 file. And this is where it's located. So the question is, can LabVIEW call functions from libc? And the answer is, of course it can. You just drop a call every function node and you can go to town. So if you are doing this like on a Linux RT target, you don't have to search for the library. You just put the library name in because it's in search path, it's going to find it. So for example, you can do things like call the string length function and pass it a LabVIEW string, and it'll give you the size out. It'll say, hey, that's a 12-byte string. So it works natively. You can call like C functions that way. So then the question kind of becomes, hey, can we do memory allocation and deallocation? It's cool to be able to call like string length, but can we do other things, right? And the answer is malloc, free, memcopy, all those directly work in LabVIEW. So you can actually call malloc, memcopy, free, and actually allocate pointers from the C library in LabVIEW. And they actually work like they're interchangeable with the move block functions and all that good stuff. And then the question also becomes, hey, do we even need to call into libc? And this is one of the th+things I actually came across a couple of years ago that I didn't quite know, is I'd always been calling in these libraries directly, and then it turns out, well, because LabVIEW is built on C++, it's already actually got the standard C library loaded and linked to the runtime. So it turns out you can actually call all of those same functions, like malloc, free, memcopy, just by typing LabVIEW in, and they're all available for you to use. So a quick example of what you could look like, if you had an example library, you could have like libc.lvlib, and then you could have, VIs that kind of wrap each of those function calls, and you can use them in LabVIEW as if, no different than you use them in the C application. So these are a couple of basic examples, malloc, memcopy, free, everyone's pretty aware of those. But they do function in LabVIEW, as you'd expect. They allocate memory, you can copy to and from the pointers. I'm not saying you should use these over like dsnew pointer and the actual LabVIEW memory manager, but as far as I can tell, there is like zero difference in terms of how they function and what they are each capable of doing.
I think I'm not actually sure if that goes portable Linux versus Mac, the direct call to libc.
Well, the direct call to libc is not. It does work when you have it set to LabVIEW, though. That does work from Windows to Linux. At least Windows to Linux I've tried. I haven't tried Mac, but...
I wasn't sure if the signatures on those are actually identical, because the big part of the reason that the DS pointer layer exists is to abstract that.
Yeah, well, that's why I was actually kind of surprised that it worked like that. I actually didn't know you could directly access them like that, but I kind of did wonder if there was going to be a situation where maybe the prototype of the function was different on the Windows instance versus like the Linux instance or something that might cause a problem. I haven't run into problems. I would recommend just definitely trying and testing and seeing what the functions do, and do they return the errors you expect, do they run like you expect. But what I will say is all the functions I've tried have worked fine and done exactly like they would do in C. So I'm going to go through really quick some example use cases that I did. So a couple of years ago I made the Linux RT interprocess communication library. It was for like a Woodward engagement, and made that with some of the guys on our team. And so the idea here is that it did the same exact approach. So what it did is it automatically, like I had a lot of C functions that I needed to implement to make all this interprocess communication work. So I needed to be able to, create shared memory files. I needed to be able to, create file descriptors and then create people mechanisms on there as well. So what you can do is you can actually just wrap a lot of C functions and go to town. So I made a lot of different ones. So you can do like the get clock time. So if you want to read the nanosecond timer, from your Linux RT target, you can use the get clock time, and it actually just wraps the clock get time function in C. Same thing for like sleeping. You can do the nanosecond sleep if you want to. So you can do like sleep for, sleep until. The cool thing about accessing these is that there is a slight difference in functionality than what you can find in LabVIEW. Is that the sleep until will actually let you provide a true absolute time in the future that you want the thread to wake up. So you can even say like wake up in at 5:37 p.m. and it will like I've tried this and it'll sleep for like 17, 18 minutes and then it'll just come online like at that time. So it's actually kind of cool. You can instead of just waiting for millisecond and millisecond multiple, you can actually sleep until a specific time as well. Another thing you can do. So we all know that in LabVIEW RT there are event structures. But through the C libraries, you can actually do event-based programming in LabVIEW. So these are functions that I used. I had like a pipes implementation, so I could do like a buffer transfer between C and LabVIEW, so I used pipes. But the pipes, to be able to actually respond to the fact that there was data available in the file descriptor, I had to actually use this equal function in LabVIEW to actually have it register for events with the kernel/OS, and then it would actually, you could then sleep on this equal wait function, and it would actually sleep the LabVIEW thread, and it would wake it back up when the function, when the events were provided, which is actually really cool, because it means that you can actually have like, you can basically create events or register for events, and you can actually just do it programmatically without an event structure if you want to. So all of this works. I mean, and the cool thing is, I'm about to show you in a second, is that one also, you just type the word LabVIEW in and it's available. So like that one also ran on Windows, Linux RT, didn't have to do anything separate. And all the different things, all the different structures you have to make, it happily accepts arrays of clusters, whatever you might have to fiddle a little bit with like the calling conventions and making sure you're passing the right data types. But all of these functions are available. Another good example of where the pointer library kind of was really useful is I updated the memory manager library to actually use the new memory pointer class. So what it now does, instead of returning the U64 to you directly, where you can kind of hang yourself and cause LabVIEW to crash, it will now encapsulate it for you, and then you can then use the memory manager library functions to read and write that shared memory pointer. So basically, that you allocate a block of memory that you can map to, C can map to, and then you can both share data, at dang near full RAM bandwidth between the two if you want to. Really quick, data sharing framework is the thing I've been working on for Veristand. The way this works is it's a framework that does a lot of memory management, and I made that memory manager library almost specifically for this application. So the reason the memory manager library has been really beneficial is because, kind of like going back to the strict typeness thing I mentioned before, is it allowed me to build a framework that doesn't care at all like what data I'm touching or what type it is. It's all void pointer memory allocations, void pointer memory copies. And the way I do that is I basically inherit from my pointer class to create a buffer class. And then from there I have 3 different categories of buffers. So we have like our inline buffer, intermediate buffer, and string buffer. So the whole point of the data sharing framework, just to kind of give you a quick overview, is that it's designed to share data easily from a Veristand system. So it'll take your Veristand channels, convert them to some kind of compacted string buffer. So it takes your double channels and turns them into other types for you. And then it will call some kind of different transceiver class. So whether it's a UDP transceiver, reflective memory transceiver, PXIMC transceiver, whatever technology you want, it will take that and then send it across that technology for you. So the cool thing is the inline buffer encapsulates the inline engine channels directly, which means that I encapsulate it with that encapsulate function I showed before, which means that when I dereference that pointer, I'm directly reading the channels from the Veristand engine, which is actually kind of cool because that's actually something that current custom devices actually can't do. Because the custom device API itself also does a move block to get the data from the Veristand engine to a double wire for you to actually process. So in this particular case, with the inline buffer, if you actually have something that can utilize the U64 pointer directly, like a C function that you can actually pass that wire to yourself, you can actually do true inline execution on your Veristand custom Veristand channels that you couldn't even do in a custom device now. Because right now, it has to do a memory copy to a LabVIEW wire to actually allow you to process that. But with the pointers, if you have a C function, you can actually just, without any memory copies, edit and execute on that data. The intermediate buffer is there for asynchronous calls, so what we do is we just duplicate the inline buffer to an intermediate buffer, and then pass that to the async thread so that it can play with that all day and not have to worry about touching the inline channels while the Veristand engine is continuing to execute. And then, of course, the string buffer is just there to capture the different size converted buffer. So the cool thing that the framework allows is to make memory copies more efficient in the framework, what we do is we have the notion of a transfer group and a transfer. A transfer is just something that has a buffer behind it, so we're going to do some kind of transfer across some protocol, and then the transfer group lets us group these together to kind of do them together. And the way we do this with more efficient memory is what we do is we actually just allocate one big buffer for the entire transfer group, and then I use my subset function to actually create little subset pointers for each of the transfers within that. And then I distribute the subset pointers to each of the structures that are actually going to utilize and execute on the transfers themselves. And so they'll be able to take those pointers, execute on the data that the pointers point to, not even knowing that it's a part of a larger structure, right? And so the cool thing is that allows the people, making plugins, the users of the framework, to interact with individual buffers, not even knowing the structure behind the scenes. But then on the other side, on the engine side, the framework side, all of my memory copies can be done with single operations. So instead of having to do a copy per transfer or per class object, I can just do a single copy for the whole thing. And because that pointer encapsulates all the stuff, the subset pointers within it, all the data comes along with it, so, which is nice.
Are you going to wrap on the next one?
What?
Are you going to wrap on the next one?
Yes. Really quick. So the same concept applies for status pointers. I'm not going to go there as well, but the idea is you can allocate a bigger block. So if you have, like, say, multiple asynchronous worker threads, and they all have, say, like just a U8, I don't know, state indicator, you can allocate a single array of U8s, basically using this pointer operation at the framework level, and then distribute individual scalars from that to the worker threads, and they can update their state to the scalar pointers. And then all the framework has to do to see the entire states of all the processes at one time is just do one single memory copy of that base pointer. So it kind of lets you do interesting memory style, management yourself, right? Like doing that with, say, like a string-based DVR, right? A DVR to a string, which is kind of the same idea, right? You can't really segment the memory of the DVR and then have different things access it in their own way without them all locking the entire structure. So that's kind of where the pointer thing can be kind of beneficial, is that because it doesn't lock in situations where you don't want it to, it can make some multi-threading architectures pretty good. And then pointer versus DVR, we kind of already talked about some of these. The pointer is more loosely typed, so it doesn't actually have a notion of type, whereas the DVR is strictly typed, like most things in LabVIEW. There is no arbiter for the pointer unless you use the protected function, but the non-protected functions don't try and do any kind of protection. So they're made so that if you want to access the pointer without any kind of protection, you can. The other thing I want to point out is a lot of people need to understand this as well, is that the pointers, they're always going to be volatile. So from like a C or a Java perspective, does anyone here kind of know what the volatile keyword means when you add it in your code? Most of you probably do. I'm sure most of you do, yeah. Does anyone not know? Okay, well, sorry. So the volatile keyword is basically a way of saying, like, don't ever let the data represented that's been keyworded by this volatile keyword, don't ever let it stay in the CPU cache. Always make sure that it goes back to DRAM, because it's a global resource that other threads, asynchronous threads, may be accessing. So the thing is, the pointer operations, they always going to be volatile. That when you do a memory copy with the memory manager library, it is doing a copy in DRAM, which is interesting because a lot of people, what they can do is fall into some of these pitfalls, which is where you try and use the pointer class like it's some kind of register or like a scalar that you might have in your for loop. LabVIEW does not optimize that like it's a scalar. It's not going to treat it like some variable that's local to that for loop, because it's a pointer, it's a global resource that could be written from anywhere, right? And so if you were to try and use that like a local variable, basically, you're just going to see really bad performance, because it's going to be doing full DRAM accesses every time it touches that variable. So the thing I just point out is that the whole point of the pointer thing is it's not in any way meant to replace DVRs. In fact, they kind of coexist in very different ways. They both kind of have their pros and cons. So I think the pointer works really well for working with other languages, sharing data between processes. That's where it's really, really powerful, just because you can natively kind of do it like C or do it like the other applications expect. And that would be about it. So I'll go ahead and cut now, because I think we're running out of time. But with that said, though, do you guys have any kind of questions or thoughts or anything like that?
So what is the difference between the DVR and this library regarding race conditions? Like you have your Mutex, right? And if one of them decides to lock it for a long time, this guy is going to have issues?
Yeah.
There's no priorities?
Well, there's not priorities in this particular level of, do you mean like real-time priorities? Yeah. Or like inheritance and stuff like that? Well, that's typically going to be done by whatever structure you're running. So if you're running in like a time loop or a time structure that's at a set priority, if you have something waiting, like I don't have to, in my code, elevate the priority. That's supposed to be done by the actual LabVIEW